So let me come to what is supervised learning. So in rest of the lecture, whatever is left, we'll only talk about supervised learning. I'll try to give you an intuition, but I'll not intuition. I'll try to give you the clarity between regression and classification and what is supervised learning. Probably in the next lecture or whenever I start unsupervised learning, we'll talk about unsupervised learning. Fine. Okay. So what is supervised learning, right? So supervised means that you have some supervisor on top of you who is making you learn. Okay, so this is very similar to the setup that we have right now. For example, you are learning, right? You are the learners, right? So you have us to teach you, right? So we are your supervisors in some sense that we are basically teaching you, we are course correcting you, we are solving your doubts. Wherever you are making mistakes, we are explaining you, okay, this is not right, this is correct, or this is not correct, right? So it's basically that you are learning in presence of a supervisor, and that supervisor happens to know what is correct and what is not correct, right? So in terms of data, what is correct and not correct comes from something called as label. You will see this word very often. What is label? Okay. So basically, label basically tells you whether what's the truth. What's the truth? For example, suppose I have an image of a cat. Let me see if I can draw an image of a cat. So I have a cat. Okay, so this is some image of a cat, right? So what's the truth of this image? So this image is of cat, right? So the label is cat, right? So I can not say label is dog, right? Because this is definitely not a dog. Let me make it more nice. Okay, so this is an image of a cat. So the label, the truth associated with this particular image is cat. So basically, what it actually is, the ground truth is called label. Okay. So whenever you have that kind of ground truth present, so there's another term that you will see very often, ground truth. Basically, what it really is. Right. So this image is of a cat. So the ground truth is cat. So whenever you have like this kind of labeling present or this kind of truth present with you while you are learning, uh, you call it label data. And whenever you learn from label data, right? So suppose that this cat image is there and the label is also there. So the image is cat, right? Now suppose I have a dog. I'm pretty sure I cannot draw a dog. Uh, right. Let's imagine this is a dog, okay? Looks more like a pig, but let's just imagine this is a dog, right? So this is a dog, right? So the ground truth for this is dog. The label for this image is dog, right? Or this cartoon that I've drawn is a dog, right? So if I'm going to use this plus this plus this to learn, then it is supervised learning. It means that you're using the ground truth to learn. And you can learn without the ground truths also, right? So that is something that we'll talk about later. But just understand that right now, for example, if you're learning some course, right? And suppose you're giving a quiz, right? Um, so there is a ground truth associated with every question, right? There is a right answer to that every question, right? So that ground truth basically guides you whether you're going right or wrong, right? So you attempt a quiz and then you answer that question. And suppose that how do you know that you're wrong or you have to make course corrections? You will only know when you look at that correct answer. So that correct answer is basically a label that you're using to learn from, right? So you're learning from that correct answer of the quiz. You make a mistake on that, right? Similarly, whenever we have the ground truth present while we are learning, it's called supervised learning. And learning from label data means that you're uh, basically learning in a supervised learning paradigm. Fine. Okay. So for example, now have all these dogs, right? And all these cats. right? So you and me know cats, but machine doesn't. So we'll have to allocate the labels to this. So I have to give the label as cat, 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 cat here, right? And this is a dog, dog, dog. So this is dog, right? So this is data with its label, with its true label, with its ground truth. Okay. Now I have shown you all these images. Can you tell me what this is? Oh, you guys know this is a cat? Okay, I didn't know this. Okay. So this is a very famous, I don't know if you guys have watched this Friends episode. I am a very big fan of Friends. I know all the dialogues by heart. So there is this one episode where Rachel gets this cat. Okay. And Joey and Ross are like, what the hell is that? It's not a cat. Right? So I also didn't know that this is a cat. This is actually a very special variety of cat. It's called Sphinx cat. Fine. So another example where humans can make mistake. I did make mistake. So I don't know if you have watched this episode. If you have not, watch it. Only point I'm trying to make here is that though you guys are able to identify this as the cat, if I was seeing it for the very first time, I will be pretty sure like these two guys that this is not a cat. Okay. So even if I give this example and this example for my machine to learn or for a kid to learn, and if I just ask this, what is this? I'm pretty sure a lot of guys will make a mistake if they've not seen this cat before. You guys already have seen the uh, cat before, so I'm sure that your model is already trained on this particular cat. But suppose I was showing it to a 5-year-old kid who has never seen this cat, right? This looks more like a dog to me, to be very honest, right? Can you see this? It doesn't have whiskers. It has this nose, right? So for me, it was like a dog. So if I was giving this information to the machine or a kid to learn, just this information, okay, I think a kid will not be able to classify this as a cat like me. Hmm. Okay. So Rohan is saying that you guessed it, but he's never accepted Chihuahua as a dog. I think it looks more like a rat. Yeah, that's what. Yeah, so suppose, so there's a very good point that Bharat made here, right? So all the images that you see here, right, they have a fur on them, right? While if you look at these, right, I think Dalmatians don't have a fur. They don't have a very heavy fur. Similarly, I think Chihuahua also doesn't have a fur, right? So if somebody who is trying to learn, so whenever I give these images to people to learn, right, they can learn different attributes of this and to, do the prediction whether this is the cat or this is a dog, right? So one very distinctive attribute can be the eyes, right? The eyes of a dog and an eye of a cat are very different, right? They have like this green color eyes mostly, right? While dogs don't have that, they have like black eyes. Similarly, the nose that they have, right, it's very distinctive for cats and dogs. Another thing can be that cats are always furry, right? Or at least in these images which I showed to the machine or like a baby of 5 year old, not a baby, a kid of 5 years old, the cat was all furry, right? Though here Dalmatian and this are not furry, right? So it can happen that when they look at it, they think that this is a dog. Okay. So, because it doesn't have a fur like these cats have, obviously the eyes are a distinctive feature. I probably should have colored the eyes. But if only this data is there, I don't think I was not able to distinguish whether this is a cat or a dog. But good, you guys are. You have some prior information on that, I'm assuming. Fine. Okay. So, uh, so just a meme around when you are not able to recognize stuff that you have not seen before. Okay. So I've been talking about training the machine, making the machine learn. How do I do that? Okay. So how does the supervised learning work? So I told you that we use label data in this, right? We use ground truth, ground. ground truth or the label data. Fine. So there are two phases of a supervised learning mechanism. So two phases are, I'll just write them here. So supervised learning. Learning. So they have a phase called training phase, right? In which you train your machine, right? And you do some evaluation while doing this training, basically evaluation. You'll do some evaluation and then you go back and do the training. Okay. So evaluation. So basically you will compute some evaluation matrix, not matrix, metric, right? For example, if I am training you, I will give you quizzes and then I will look at your marks, right? And when I look at your marks or you look at your marks, you will realize that you are making a lot of mistakes. So you will go back and train yourself again, right? You will reread that concept, right? Similar to that, you have a training phase, right? And then there is a testing phase, right? Testing phase is basically your gate exam, right? Here you don't have a way to go back and correct your answers, right? So whatever you do in this, you do. It's like your final performance, right? So you will only do performance evaluation. Like how good are you doing? Final performance, right? Uh, and there'll be some final AIR that you will get. I'm assuming all of you get under 50, but let's see. Okay. So let me explain training phase for you guys. So I want to train this machine to recognize, to differentiate between the cat and the dog. Okay, so I will have to write some goal. Okay, so my goal is differentiate between cat and dog. Okay, so I'm showing these three images of cat to this machine. How I'm showing this is not a concern right now. I have talked about this in the lecture, linear algebra lecture, but I'll talk about in a while, like how I'm going to, feed an image to the machine. But let's assume that there is a way to do that and you're just doing that. Okay. So you are basically taking this cat image and this is the label. Okay. And similarly, you're feeding this cat image and you're feeding this label and you're taking these dogs and feeding this label, right? So you're feeding this data to this machine. So for example, I want the robot to distinguish between the cat and the dog so that maybe I don't know. So to not to allow cats inside the house because I don't like cats that much. I like dogs. So probably just to allow dogs, I'll train my robot to, not allow cats inside the house. Right? So this is my goal. So I'm giving this to this machine and this machine needs to basically distinguish between the cat and the dog. Fine. Now observe that each image and is its corresponding label is the input here, right? I'm sending the input data. So this is one input. If I have to talk about, this is one input, right? This is second input. This is third input. This is fourth input. This is fifth input, right? And this input, right? One input is called a data point. Data point. So some of the terminologies that I'm putting here so that you understand. So one instance, right? Some data with its corresponding label is called a data point. Fine. So we send this data point to the machine to learn. Fine. Okay. So let's do a quick quiz. How many data points are there in this data? Suppose this is the data. How many data points are there? Okay. Others? Okay. And how many different type of labels are there? Okay. Fine. Okay. So I'm sending this label data to my machine. Fine. Okay. Guys, I'll suggest you please reply to me privately and not to everyone, so that I can monitor everybody's answers. Okay. Fine. So I have 5 data points here, right? Now I can use the word data point. Now you understand what is a data point. So I have 5 data points here. So data with its corresponding label is sent to this machine, right? And this machine does some magic, some black magic I'm doing here. And this machine is learning something, right? So it should be able to distinguish between a cat and a dog. Fine. Okay. Now let me talk more about the terminologies, right? So you will see us using X for data, right? X is usually used, this capital X is used for data, the training data that we have, right? This basically is the non-label part of the training, okay? And the Y is used for label, right? So X is the data part, like for example, data here is the image and Y is the label. So the label is cat and dog. So Y will be that, right? So here we have 5 data points, right? So I have X1, X2, X3, X4, and X5, right? So we use subscript for data points. This will be common in our lectures. Subscript will be used for representing the data point, like what is the number of the data point, right? For example, if I have to talk about is X3 a dog or a cat, right? So X3 is a dog, correct? If I have to talk about, say, X2, is it a X2? What is the color of X2 cat? It's black, right? So subscript basically tells me what data point I'm talking about. Like, so for example, ith data point, X subscript I, fine? Similarly, the corresponding labels will also have the subscript. Can you observe the subscript? Right? So these are just standard representations, standard notations that we are going to use. Fine. So X1, X subscript 1 basically is representing the first data, right? And Y subscript 1 is basically its corresponding label. Fine. So there is a one-to-one correspondence between this X1 and Y1. Similarly, I have one-to-one correspondence here. Similarly, here, and here. Okay. I have a question. So the ground truth and label data is same, or do they carry different meaning in ML? Okay. So ground truth is same. Okay, it's usually the same. Let me differentiate between these two if we can. Right. So ground truth and label data is actually same. Is or the label, right? So suppose that so understand ground truth as like this, right? So the label of the data that you receive is the ground truth. Ground truth. Obviously, there can be errors. So your ground truth might not be always true. For example, suppose somebody has collected like 1 million images of cats and dogs, right? And suppose they happen to come at this particular image. Where is that alpaca image? I think here, right? So suppose you have it in your database, right? And somebody was manually labeling it. Okay, manually labeling it means that it was manually telling that this is a dog or a cat or an alpaca, right? So here the human can make error in making the labels, right? And how is this data labeled? Let's talk about that. Where do you get the label data from, right? So label data in this whole world is very small, right? The amount of data that is actually labeled is very small. People are actually paid to label data, right? So the company that I worked for, we used to pay doctors who had like an MD to label the data. And it was a very costly business, right? Because we want the ground truth, right? Obviously, they can make mistakes. So your ground truth might actually be not the actual reality. For example, suppose some student was labeling this. I went cheap on my labeling business and I was like, okay, let me employ some fifth grade student to label this data, right? They might not have seen an alpaca before, right? Or they might have seen an alpaca before or something. I don't know. Probably this, right? If I am asking a student to label this, and if they're not seen an alpaca before, they'll probably call it as a sheep, right? Or they maybe call this also a sheep, right? So I don't know, right? So the labeled data that you're receiving, on which you're training, or in which you are, testing also, we'll talk about testing phase, can have errors, right? So the ground truth is still what you receive or what you use to train or test your data, but that ground truth might not be the actual reality, right? So we always have some error in labeling, and we assume that whenever you will study bias variance trade-off, you will basically see that we always assume some error is there. Not even bias variance trade-off. I am not sure where we are going to learn this, but you will see that we always keep in mind that whatever truth, the ground truth that I've received in my data might not actually be the reality. Fine. So I'll give you an instance. This happened. So you are training for predicting a very rare disease. Okay. So detecting that disease itself was a very tedious task. Like a doctor had to sit for like hours, examine the notes of that patient and label that, right? And it so happened that whatever initial data that they labeled, we were getting a very bad performance on that. And then the supervisor that we had, he was again an MD. So he realized that probably the data labeling is incorrect. So the doctors went back and then relabeled the data, right? So the ground truth or the label data that we were using to train that particular model, that was not correct. And so the errors can be there. It's not the true reality. Okay. So you have to understand that this ground truth and this label, right? These are basically features of data. Okay, let me not use features. It's a special meaning in machine learning. I will say it's a property of the data, right? And this ground truth can be wrong. This labels can be wrong. Labels can be wrong. And we call it noise. We call it noise in the data, or the data is called noisy data. Fine. Have I answered your question, Bhavesh? Okay, fine. So let's come back to this. So I was telling you that we use X to usually represent the data and Y to represent the actual label associated with it in the data. Fine. Okay. Now, okay, before that, any doubt here, like how we are representing? So only thing that you have to remember is subscript basically tells you which data point is that, right? So ith data point is xi, yi. Okay. So let me add this data point. So I told you the data, image data that I was using plus the label is called a data point, right? So data point is xi and yi subscript, right? Observe the subscripts. And this combined together is called a data point, right? So it's the ith data point. Right? Data point means a point in your data. You'll have a huge data. I used to work with a 9 million ECG ka data, right? So every ECG in that with its corresponding label that we used to come up with was a data point for us. Fine. Okay. Now I'm hoping data point is clear to everyone. Okay. So Shubham is asking subscript means feature. No, Shubham, subscript means the data point number. Okay, so for example, okay, let me give you one more example here. Okay, so I'm introducing something called as tabular data here, which is we'll see later. So this is my tabular data. Okay, and suppose I have this. Okay, let me come up with something called as hair length. Hair length. Okay, and this is basically gender, right? So hair length long is usually associated with females, right? Or let me say, I'm just cooking up this example, okay? I've never seen this data before. So say 3 feet, right? The hair length is 3 feet. Definitely, most likely it's going to be a woman, right? And say like, I don't know, 2 inches is a male mostly. Similarly, 2 feet female, right? So this is my data, okay? So this particular thing that I have here, right? This one is my X1 and Y1. Okay, so X1 is 3 feet and my Y1 is F. Okay, so this is my data point, and this subscript is basically represent what is the number of the data point, right? So this is the first data point that I have, right? So one is subscript is representing the first data point, right? Now, if I have to talk about this this third data point, right? This one, third. So this will be x3 is equals to 2 feet and y3 is equals to f, right? So this is my x3, y3 data point. So this is my third data point, right? So the subscript is basically representing what is the number of the data point. What is the like ith data point, right? Feature, I'll introduce you what is a feature. Let's not go there. Okay. Ith row in a matrix of data can be said like that. Correct. So this is our tabular data, right? So this is our tabular data. So this is the first row, right? This is the first row. This is the second row. This is the third row. So if you look at it like a 3x2 matrix, right? If you look at it like a 2x3 matrix, so let me convert it to a matrix, right? So this is the matrix that I'll have. P 0.2, 2 feet. And let me call female. Female is basically 1 and male is basically 0, right? So I'll have 1, 0, 1. Okay, because I have to represent this data in form of a number for the machine. So I've converted this to a matrix. So this is a 3x2 matrix, right? So the ith row is my ith data point. Ith row is ith data point. So actually, the convention, right? So it depends how you use it. A lot of people use it like this, and some people will use the superscript as the uh, index for the data point. It doesn't really matter. You have to stick to just one. Uh, Okay, so basically, you will see multiple. So Rohan, I'll answer your question. So Rohan is asking that, is this the standard convention? So actually, in general, there is no standard convention for this. I don't know this TM Mitchell books. I have not read it. I have been referring Bishop. There is a TensorFlow book and Tepshirani, Elements of Statistical Learning. And I think they use subscript to represent the data point and the superscript to represent the feature. So whenever Gate will give you this question, right? Whenever Gate will say xi, yi, superscript, subscript, they'll tell you what that means. Okay, so you don't have to get confused. For these lectures, we will use subscript for representing the data point and superscript for something called as feature, which I'll come to later. But whenever Gate will give you the question, they will specify what is the meaning of subscript and superscript for you. Fine. Okay. So Shubham has a question here. 3 feet here length is a feature. Yes, Shubham, you're right. I'll come to the feature in some time. Fine. Okay. So I have explained the data points to you. Now you know the convention. You can use superscript, subscript, nothing. It will be specified in the question what is the meaning of superscript and subscript for you. Gate will at least do that. I'm not sure. You will find it in standard like in questions that you'll see online. So not sure about that. Fine. Okay. So I started with teaching this robot to distinguish between the cat and the dog, right? And there was a purpose I was teaching this robot something, right? I wanted to use the robot that learning, whatever I had given that learning, to use it, right? Because I wanted to ban cats from my house, but I wanted to allow dogs inside my house, right? And suppose the robot is the one who opens the door for me. Then I want the robot to identify whether it's a cat and a dog, and it should basically restrict cats, right? So whatever I'm teaching to that particular machine, I want it to use it later, right? Otherwise, why will I spend my time teaching the machine if I can't use it later, right? So the testing, like whenever I'm going to use whatever I've taught to the machine, is called the testing phase. Okay. Or this is where, the machine basically, you basically put it to use. You basically start using it, and you will call it in industry terminology, if I have to talk about, this is called production phase. So it's actually deployed is another industry word. So basically now whatever customers you have are now using it. Now this particular robot that I was training for my house, it will start predicting dog and cat. Okay. So now can you see that these are not the images that I trained it on? Let me go back and show you where I trained it on. So I trained it on these images, right? And now I'm testing it on these images. Okay, so this is called testing phase where you actually test it. So now the machine will learn. There is a process on how the machine learns. We'll talk about it later. It's just understand there is a mechanism for a machine to learn. Fine. So the machine has now learned. I have trained it well. Now new dogs and dogs and cats will come, and I'm hoping that my robot will be able to differentiate between dog and cat, and it will not allow cat inside. Fine. Now suppose that I come home one day and I see this particular cat sitting on my sofa, right? So I will know that something is wrong with this robot because it allowed a cat inside the house, though I had specifically told it that don't allow the cat inside the house, right? Differentiate between a cat and a dog and don't allow it. If this particular cat is sitting in my sofa, I will have to rewire this particular robot, right? I'll have to retrain it because now it's making errors in production, right? Obviously, there is something called as tolerance. Everybody has some tolerance, right? So we have some tolerance level associated. Like, okay, maybe I can say, okay, I was also confused whether this is a cat or a dog. So maybe, okay, fine, if this robot was not able to detect this cat or a dog. Now, suppose my robot fails on this, right? I will be worried because this ginger color cat is very common, right? At least in my neighborhood, I see this cat every other day. It's not the same cat. There are multiple cats which look like this, right? So if the robot is letting come this particular cat inside, it'll let the other cats inside as well, right? Though this particular cat, Sphinx cat, is rare, right? So I might not be that worried about if my robot makes an error on this. But if this, right, which is very easy, which is like a ginger cat, anybody should be able to recognize this very easily, right? So I will be worried probably here, right? So I will say probably less worries if I have misprediction on this, but I will be more worried if my robot makes mistakes here, right? And then I'll have to do something called as rewire. Rewiring is not a standard term. Rewiring is basically you're just retraining the model or you're retraining the robot. I'll again like introduce this cat images. So I'll go back and see that probably I did not introduce this cat images to my so there was no ginger color cat in my training data, right? So probably that's why the machine made a mistake. So I'll add more images of this ginger color cat, and my machine hopefully will learn better, right? So also observe that in the testing phase, you have unseen data. Unseen data means something that you have not seen before, right? That's like a true test of a model, something that the machine has already not seen before. And this is something called as unbiased estimates. It's a standard terminology, unbiased estimate. Unbiased means that suppose I give you a question in class. Okay, I solve the question with you in the class, and I give the same question in quiz, right? Is that a correct estimate of your knowledge? Yes or no? No, right? So the data that I'm training you guys on, if I give that in the quiz itself, it's not the correct analysis of how much you have learned, right? Because you have already seen that question. So most likely 90% of the times you will be able to solve that. The true test of your knowledge, the true test of something that you understand, the fundamentals of you understand is something on a very modified question, right? So I'll try to modify the question. I'll give you a tricky question to answer, right? Similar thing happens here that whenever I have to do an unbiased estimate, right? So whenever I give you the same question in the quiz, right, it's called a biased estimate because you have already seen that data, right? So you are already biased towards that data because you already know it. I should get an unbiased estimate to really know how you're doing, right? So I have an analogy prepared for this. I'll come to that in few, like I think 1 or 2 slides. Um it's related to your mock test. Okay, so I'll come to that. Uh, okay, so I have to do an unbiased estimate. I have to basically show you questions which you have never seen before, right? Or which are new to you, so that I can get a real sense where are you standing right now, or how much have you understood, right? So that's the same thing that we do for the machines as well. Fine. Okay. Okay. So models can make mistakes. So this was the testing phase, right? So just introducing with you to you with the testing phase, like what happens in the testing phase. Um, I've not talked about what really happens in the testing phase and what really happens in the training phase. Probably I'll take that up tomorrow. But just understand there are two phases: training phase and the testing phase. Okay. So models can make mistake. Okay. So models are more likely to make like models can make mistake, and we love to get an estimate of that. For example, you guys also make mistake, and I love to get an estimate of that. And that's why I give you a lot of quizzes, right? Because I want to understand how much you are learning, right? I can't go to every student and ask, okay, every concept. I can't take a Viva, right? So quiz is a method for me to test you, to get an estimate where do you stand, how much you have learned so far, right? Similar estimates we do for model as well. And there are two types of estimates that we do. One estimate happens during training phase, right? For example, your quizzes, right? And one estimate happens uh, in your test phase, or there is a better term for this. It's called validation phase. Validation is like I'm validating whether you've been trained enough or not. Okay. So now let me come to the analogy that I wanted to give you. How can, okay, a very good question. How can error happen in training? Okay. So error can happen. Uh, Suppose this data is there, right? Let me copy this. There. Uh, Okay, so question is that how can training data, like while you're training, you can have error. Okay. So very good question. Let me just take that. Okay. Okay. Right. So now suppose this is my data. Okay. So I'll give you, there can be many how. So the question is, how can training have error? Okay. So let me write these labels for this. So there is a dog, there is a dog, there is a dog, this is also a dog, this is also a dog, this is a cat, this is a cat, this is a cat. Okay. Now I have two data points. Let's assume that there is a whisker here. Okay, so this is slightly different. Sorry, let me add the whiskers here. And this is just one example. There could be multiple reasons. I'm giving you just one example, just an intuition why it can happen. There are multiple reasons for why can we have errors in training data. Multiple reasons are there. We are just discussing one of them. Okay. Now suppose this image is slightly modified, right? But this is marked as cat. And this here, which was not modified, this is dog, right? Right? So here you have noise. This is noisy data, right? Now, when the machine learns, right? Or even if you and me learn, right? If I see these two images, one is labeled as dog, one is labeled as cat. So I don't know what really to predict about this, right? So I can make, matlab, there are high chances that I will predict it incorrectly, right? For example, I can say it cat and I can say it dog, right? Or I can interchange that. For example, or maybe I will, when I see this image, I randomly answer a dog or a cat, right? I don't really learn anything about it. I just say like 50% probability, or I toss a coin and I say, okay, it's a dog, right? Whenever the head comes, I will say it's a dog, right? Because I can't really differentiate between these two data points, right? There is not much differentiation, right? Visually, right? Hence, the same thing applies to the model as well. When there are two data points which are very close to each other, but they are completely different labeled. Okay, they are very different. Like this is dog, this is cat. There are chances that the model will not learn this properly and it will make mistakes here. Okay, so it's not something that uh, the model is wrong. The thing is that the data that you have is noisy, and we always have noisy data, right? We always have noisy data. Like 99% of the times, uh, we'll have noisy data. Right? Because this data is collected by multiple ways. This is labeled by multiple people. So they are tend to have wrong labels. And when they have wrong labels, that gets, the model doesn't learn that well. So it will not be able to differentiate between cat and a dog, these two images. Have I answered your question, Rohan? Like, how can you have error in training data? Okay. He is asking non-representative data. Yeah, probably what you're saying is right. If I understand correctly, non-representative data is like it's these two images are not like a true representation, whether it's a cat or a dog, right? So I think what you're thinking is right. Fine. Okay. Okay. Now let's talk about further classification of supervised learning. So there are two types of algorithms in classification, in supervised learning. So the one is classification, the other is regression. Okay, and there are only two types of supervised learning. Either it can be a classification or a regression problem. Okay, and we'll see how do we differentiate between classification and regression now. Okay, so the problem that we have been seeing so far, like assigning whether it's a cat or a dog, is actually a classification problem. Okay. So here there are two classes. right? So here we have a dog, right? So this is probably my class 1, and this is my class 2, right? So there are two classes I am allocating these images into, right? While predicting or even while training, there are two labels associated with this data, right? It can either be a cat or a dog. There is no third label, right? So this is a two class classification problem, or it's also called binary classification problem. Binary means two, right? So this is a two class classification problem. I think in your course, you only have two class classification. We'll see. I think regression, we have multi-class, multi-regression, but I think we'll cover multi-class classification also, right? Or this is also called binary classification, right? You will see a lot of people use binary classification or two class classification for these. When you have just two classes, right? So let me give you some more examples. Suppose you have an ECG, and I actually worked a lot on ECG. So you will see my examples are mostly ECG oriented because that's what I worked mostly on, right? So ECG used to look like this. And given that ECG, you have an algorithm, which is like disease prediction algorithm. And this can be any disease, okay? So for every disease, we used to have a different algorithm, right? And it predicts whether you have disease or not. Have disease, doesn't have disease. Right? So is this a classification problem? What are the classes? So I'll give you, this is a classification problem. Tell me what are the classes. Okay. Okay, everybody is clear that there are two classes, whether you have the disease or you don't have the disease, right? Okay, now let me have it ahead. Fine. So this is binary classification problem, as I already told you, because there are just two classes. You can have multiple classes, and those problems are called multi-class classification problem. Okay. So can you tell me how many classes are there? So I have these. I'm sorry if somebody's afraid of snakes. Three, right? So what are my classes? I have cats, dogs, cat, dog, and snake, right? So I have three classes, right? So these classes are fixed, right? It's either 1, 2, 3, or it can be n, right? Even it can be 1 million also. Doesn't matter. If you are binning them, you can understand them whether if you're binning means you're putting them in a bin, or you're putting them, suppose there are 1 million bins. You're taking one example, you're putting it in the bin. If that's something that you're doing, it's a classification problem, okay? So binning them in some n bins. Okay, and this bins can be any number. There is no restriction. Even it's a million, it's a bin. You're binning them in a million bins. Fine. So this is a classification problem. And anything which is not a binary classification problem is a multi-class classification problem. So there are multiple classes now. Okay. So this is multi-class classification problem. Let me just remove this one. Okay. Fine. Okay. So that's about classification problem, right? So you have some images or you have some data, and you are just binning them in some groups or some bins or some classes, and that's your classification. And classification says a lot, right? Classification. So you're putting them in a class. We'll see some examples. I think you will not be able to answer them. Okay. So that's about classification problem. So if you have a classification, like if you're pinning them or if you're putting them in some bins, that's classification problem. Okay. Let me give you one more example. So suppose I have this data. Okay. I have this data. I don't know if you guys have seen BMI scales. And I'm not sure what exactly is the classification. But suppose your BMI is 22, then I think over 26 and this, right? So here there are Three classes. You are either underweight, underweight, right? Which is here. Okay, if you are less than 22, you are underweight. You are normal if you are between 22 to 26, and you are overweight if you are above 26. Okay, so tell me if this is my class. Suppose I have a weight. Okay, I have weights a lot of people. Say I have 46, or say I'll have BMI. Okay, I have directly the BMI. You have BMI, and you have to predict some label. Predict label, right? Suppose you have 22, right? You will probably call it underweight, right? You have 21 underweight. You have 23 normal. You have 28 overweight, right? Now tell me, is this a classification problem? What are the classes? How many classes are there? Three class classification problem. Okay. Three classes, right? So this is a three class classification problem. Problem. Now I want to introduce something which I was not planning to introduce. I will introduce something called as decision boundary. Okay. This. Right. So let me introduce something called as decision boundary. Okay. So something that we are going to talk about is decision boundary. So decision boundary is nothing but a boundary the classifier will create so that it can bin the data. Okay. So what I mean by this is there are two decision boundaries here. So all of your data will lie on this line, right? What kind of data is this? 1D, 2D, 3D, 4D. What kind of data is this? So if I'm going to plot this, right? So this 22 will come here, right? This 22 will come here. Say I'm calling this A point. This is A, right? This 21 will come here. Let me call it B. This 21 will be here, right? This is B. Then I have 22 here. This is 20. This is C. This is C. And this 28 will come here. Right? So this is my D probably. This is 28, right? So I have 4 data points, right? Everybody agrees I have 4 data points. And somebody has already learned this classifier, okay? Somebody already has this, and it so happened that this particular classifier learned this, that there are 3 conditions here. So if you are less than equal to 22, you are underweight. If you are between 22 to 26, then you are normal, right? And whenever you are greater than 26, greater than equal to say 26, you are basically overweight. Overweight, right? So these things, right? Suppose I have not feed this, I have not coded this up. This is something that machine already learned based on some data that I provided it. And machine has the capability to learn. This is a very simple data for a machine to learn from, that, okay, what is these decisions or these 3 instructions, right? So suppose that machine learns this, right? So what it'll do is, and this is an imaginative concept, it will create something called as decision boundary. This is for something us to visualize so that we can understand how the decisions are being made by the machine. This is something that machines don't automatically do. We just understand. This is for our understanding how the decisions or the predictions are happening for the classification algorithm or for any algorithm. So these two, right? these are decision boundaries, right? So whatever is between this, right, will be normal, right? Whatever is in these two boundaries, it's normal. Whatever is here, right? Whatever is here is underweight. Whatever is here is whatever is here is overweight, and whatever is here is underweight, right? So you can see that imaginary construct here, these boundaries are being created, that whenever you have data here, it will be normal. Whenever you have data here, it will be overweight. Whenever you have data here, you are underweight, right? So these are called decision boundaries, right? How the decision is being taken by the machine, right? Clear? What is the meaning of a decision boundary? We'll do one more example. It'll become clear. Okay. Now let me plot some data for you, and I'll ask you, tell me where will be the decision boundary. Okay. Now suppose I have some data and it plots like this. So I have some stars and they belong to one class. And these are some circles, pink color circles. But probably these are like some attributes of boys and girls, right? And probably this is my girl class. So this is probably women. And this is men. Okay. So this is my second class. Tell me what classification problem is this? So these are data points associated with men and women. Some attribute is there. Probably I'll say intelligence. Right. And a lot of you will not agree with me, but I'll still go ahead and do it. And this is probably like strength, physical strength. Right. I can do this because I'm a woman. I can make such claims. Okay. Fine. Okay. So this is a binary classification problem. Binary classification problem. Cool. What are the classes that I'm binning them into? Obviously, I'm biased. You guys are right. If I'm going to do this kind of classification, I'm a biased classifier. Okay, good. You guys are learning stuff very quickly. So this is a biased classifier. Right, so this is men and women. Probably this is a biased classifier, but I'm still going to go ahead with it. So I'm plotting people with the intelligence and physical strength, right? Binary classifier. Cool. Now tell me where will be, suppose I have to distinguish between, like want to have a decision boundary. Like my model wants to, suppose a new point comes, right? Suppose a new point comes here, right? What will it be predicted as? What should it be predicted as? Okay, others, please answer. If a new point like this comes, okay, this is a new point. Okay, what should be the prediction? I have just two answers. Others, please answer. Okay. Looking at the data, Bharat, looking at this data, what should you predict? Okay, let me move this point to this here. Okay, let me have this point here. Probably, Bharat, you will be clear on this. Now, suppose the point is here. What will it be? Bharat, Varshita, why to the M class? See, all could happen, but can't you see that these are closer to these women data points? So they should be closer to women. Varshita and Bharat, I want you to unmute yourself and let me know what's the doubt here. Then why men? Why did you say men? Oh, star. Okay, sorry. Okay, sorry. Okay, you guys are very observant. Nice. Okay, let me do this. So this is big star because they are already segregated, right? Now suppose a new data point comes, I already don't know what it is. Okay, so I'll make it a plus. Okay, so this is a new data point. Okay, so it's not star or it's not circle. So, okay, so basically star and circle is representation only after they have been classified into men or women, okay? When a new data point comes, you will not know whether they are men or women. There will be some algorithm which will tell you, and then it will convert it to a circle of pink color or a star of blue color, okay? How is it noisy data? How is it noisy data? But let's talk about how is noisy data. I am hoping this is all fun, okay? Anyways, now tell me if okay, I think you boys will not agree with me. Let me have it here. Okay, this plus I have, right? I want to either make it a pink circle or a blue star. What it will be? Look at this data and tell me where do you find that they are closest to? I think I am the example, Bharat, in front of you. If you have not seen the data, so Bharat is saying he has not seen this type of data. I'm saying I am one of the examples, right? Do you not agree I'm intelligent? Because I'm teaching you guys. So I must be intelligent. Quickly answer. Oh, okay. So Bhavesh is saying, I just meant because you misinterpreted the yellow star. So it'll be just an error in training. Oh God, guys, you have taken it so seriously. No, so basically, see, whenever a model is being trained, right, it will train on the basis of the data, right? And the way it will do the predictions is based on how the data is, right? Suppose this data happen to be all the women who are very intelligent, people from like women from ISC, right? And this is normal tier 3 guys, probably, right? So if you have this kind of data and a new data point comes, right? So what is a like what is the probability that the model will predict it as a women? High or low? Okay, let's talk like that. Okay. So I have a new data point. Now this is supposed to be like all the women from ISC, and these are guys from tier 3 college probably. I'm not saying they're not intelligent. It's just that in if I take an exam, these girls will score more than these guys. And if a new data point comes, right, and the model has learn from this pink and blue data, uh, what will be the prediction for this new label point, this new data point that you get? This is new data point, new unlabeled data point. Okay, what will be the prediction, everyone? Now everybody is using probability here. Okay, cool, fine. So most likely this will be predicted as women because the data is like that, right? So it's not like a natural construct. Even if it was a natural construct, this was true. But but from this data, the model will learn like that, right? So model will learn to predict that, okay, if a data point is here, most likely this is women. Okay. Now, nobody argued that women can be stronger as well, right? They were all like, nay, women cannot be intelligent. Very bad guys. Anyways, now if I have a data point here, say a new data point here, how will it predict? Men, right? It most likely will predict men. Everybody agrees that this will most likely be men, right? Suppose a data point come here. What will happen? Men, women, men again, right? A data point comes here. Men or women. This is women, right? So can you see that there is some decision boundary here somewhere, right? Agreed? Malab, I don't know if this is the actual decision boundary if I train this data, but can you imagine that there is some decision boundary here that, okay, if people are here, if if I get a data point here, I'll mark it men. If I get a data point here, I'll mark it women, right? So there is some decision boundary that is being there, right? What happened to the points here? Say I create one here. Let's not call it star. Yes. Right? What will happen to this? Like it's on the decision boundary, exact decision boundary. Let's say there is a decision boundary. It's exactly on the decision boundary. Any guesses? Make a guess. What will happen? Okay. Others guesses. Okay. 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 Varshita, what do you think what will happen? And Shubham, what will happen? Mihir, take a guess, okay? Even if you're wrong, doesn't matter, right? There is no right and wrong answer to this. No, so the decision boundary is here, right? The decision boundary, Shubham, is here. Okay. Now this data point is lying on this decision boundary, right? And I have, oh, you guys are very advanced. You're already talking about Manhattan distance and whatnot. I've not given you all those terminologies. Just think, right? What will happen, right? Uh, let's assume that you don't have any previous memory of machine learning, and you just know that this is a decision boundary. If a data point is here, you will mark it men. If a data point is here, you will mark it women, right? Now there is a data point that comes on the decision boundary. What will happen? What can happen? What can happen? There is decision boundary. So, okay. Okay, Varshita, correct. Shubham, can you let me know what will happen? Right? So here, okay, because you guys are not able to see this. This is the data point, right? For which the machine will have hard time doing a classification. Okay. So this will basically be random. And this is where, machine will make mistakes. Because this point basically is lying on the decision boundary. So the machine will not know whether this is a man or a woman. Correct? So the machines, as I have been saying, right, from the very start, I never said machines are perfect. Though they have actually done better than human performance in certain tasks. But if it so happened that this data point comes on the decision boundary, which is there, machine will struggle, right? It probably will do some random thing. It'll either classify it as a man or a woman with a coin toss. Oh, sorry, with a coin toss. So it'll be like a random thing, right? And it'll make mistakes, right? So we can't say for sure. And when we do, nearest neighbors, I'll talk about this more. Fine. In that case, if this kind of a question comes in gate, they will tell you how to break the ties, right? They'll give you that, okay, use this particular property to determine or to break the ties. But here, it's kind of a tie. It's not sure. The model will not be sure what will happen to this men class or the women class, where to assign it. Clear? Clear, everyone? Okay. Others, please, yes, no, so that I know that everybody's on the same page. Okay, so Rohan is asking, very good question. Do we get to select this decision boundary or it gets decided implicitly? So it gets decided implicitly based on your data. Okay, so suppose this data point is here, right? And the model train, and I'm saying that this is the decision boundary. Now, suppose I add like a data point here, right? So you might see that the decision boundary shifts like this. Maybe and you will see it in SVM more when we talk about SVM. Let me use some color which is not used. Okay, so you will see that decision boundary might shift because of this one data point. So based on your training data, these decision boundaries are implicitly made by your learning algorithm. Okay, so it's again an imaginative construct. Imagine it's not imaginative in that sense. Obviously, there is some decision happening by the classifier, and it now not need not be a very it need not be like a single line, right? It can be like this. It can be like this also, right? It's just a construct. It's something that we basically try to understand that how the model is predicting. So it might not be true. It'll never, I don't think it'll ever show you the decision boundary also. Or if you can, I have never plotted the decision boundary, but I think SVM you can do. Right? Okay, so there is some way SVM. Okay, Bharat. SVM is support vector machines. It's part of the syllabus. We'll see it later. They will cover that. Okay, so Rohan is asking, so it minimizes the error, least square and modifies accordingly. Yeah, basically on some method it'll create this boundary. We don't know. I'm not worried about how this decision boundary is created. All I'm telling you is that there is a decision boundary that exists. If that decision boundary is given to you, how do you think the machine is going to make the decisions? Fine. That's all I want to talk about right now. How this decision boundary is being created, that we will discuss later. Okay, so Bhavish is asking, so we just use it to visualize, but it's internally done by machine. Would a vertical line also be correct? Yes, it can be anything, okay? You're right, Bhavish. So if there was like a vertical line like this, suppose this data point was not there, okay? Suppose this data point is not there, then a vertical boundary could have been a decision boundary. We don't know what the machine is learning, right? So it's a construct that machine will automatically create itself while it's learning the data. It's learning from the data, and we really don't have a control over it. Okay. There are things you can do so that you can ensure that it's a perfect decision boundary. Matlab, for example, if I view this decision boundary, I think this is better than this vertical one, right? I don't know if you guys can see it still. You will see it in SVM when we talk about SVM more, because there is where we talk about decision boundaries a lot. To rid of this, okay. So I think, so if the decision boundary was like this, right? Right? I think the decision boundary, this particular decision boundary was better because everything was very constrained in the decision boundary. Right now, you can, if you have a vertical decision boundary, you can see that this particular data point and this particular data point is very close to the decision boundary, right? So it might not be that a good decision boundary. We will see this in SVM. Just understand that there can be multiple decision boundaries, and sometimes we try to use these decision boundaries as a mechanism to train our machine learning model. Like create the best decision boundary is something that we do in SVM, right? So yes, it can, you don't know what a decision boundary is. For SVM, probably you can find what is a decision boundary. But for other algorithms, you might not be able to plot that decision boundary, how the decision is being taken by machine. Clear? Everyone clear? Any doubt? Okay, awesome. Fine. So this is about classification, right? Everybody is clear on classification. We have a classifier. We basically bin them into different classes, and then we have some sort of a decision boundary where the decisions are taken. Decision boundaries also happen in regression also, but I'll not talk about them in this lecture. Uh, but can happen, right? So basically, decision boundary is nothing but how the machine is taking the decision, whether it's this class or this class, right? So that's decision boundary for you guys. Okay. So we have seen classification, right? We have understood what is a classification problem. Let's see what is a regression problem. Okay, very simple regression problem. Okay. Now let me formally introduce features and tabular data for you. So people have been talking about features in this lecture and I said I'll come to it. Similarly, is tabular data. So there are multiple types of data. Okay, so there is structured data. There is unstructured data. Okay, unstructured data means there is no structure to it. For example, text, right? Whatever messages that we send to each other, or say newspaper articles, or whatever text is there on websites, right? That's unstructured data. Structured data means that there is some structure to it. So there, for example, tabular data, right? It's structured data, right? So tabular data is nothing but something which is stored in a form of a table. It's a tabular data. Okay. So this particular data I have taken from house price prediction problem from Kaggle. So if you already don't know, like you have lead code, right? For coding, for competitive coding, you have Kaggle for competitive machine learning or data science. So there you can go and find data sets. So I've taken this data set from Kaggle and it's few data points that I've taken from that tabular data. Okay. So here I have price, area, bedrooms, bathrooms, stories, like how many stories are there, like how many floors are there, guest room is there or not, basement is there or not, right? So, uh, so can you observe that I've covered price in a different color and rest of them are in different color? The reason being, price is basically something that we want to predict. Okay, so this is why. Okay. And these area, bedroom, bathroom, stories, guest rooms are basically my X. Okay, so this is X1, X subscript, superscript 1, this is X sub superscript 2, this is X sub superscript 3, this is X superscript 4, sorry, this is 4, this is X superscript 5, this is X superscript 6. Okay, so X superscript I is basically the ith feature. Feature, or you can call it attribute, right? It's basically, so this is one data point, okay? So let me draw this. This is one data point. This is data point, right? So this is ith data point. This data point has features like area, bedroom, bathroom, stories, guest room, and basement. Fine. So all of these are features. And what is the label here? What I'm trying to predict is the price, right? So price is the label here, right? Or you can say Y. Y is the label here. Clear? What is feature? Is it clear? Feature are nothing but some different attributes, different properties of that particular data point, right? For example, if I have to talk about cat, suppose I was not giving cat's image, I was giving a tabular data associated with a cat, right? So for example, I'll say whiskers. Whiskers means those mustache like things. Whiskers are there or not? Yeah, I've done a very bad job at creating this. Whiskers. Whiskers. Right? So you will see that dogs mostly, I don't think they have whiskers as much as cats have. So whiskers, cat, right? And label is basically cat, right? So whiskers an attribute or feature of cat, right? Similarly, say suppose that uh, all the dogs, all the cats in the world are ginger color, right? Let's assume, or in at least in my data set, I have only ginger color cats. So this is an attribute. This is a feature of cat or this data point that this cat is ginger in color. It has whiskers and the label is cat, right? So these are nothing but the features of the data point, and the algorithms basically learn from that, right? They try to learn from these things, right? Now, suppose that I have a dog, which suppose this is a dog, right? It will not have whiskers, and suppose all the dogs that I have are black in color, right? So my algorithm or whatever is learning from this data can create a decision boundary such that if you are ginger in color and you have whiskers, then you're a cat. If you're black in color and you don't have whiskers, then you're a dog, right? If only this data is given, right? It'll learn the decision boundary like this, right? So in this tabular data, these are features, right? X superscript 1, which is area, right? So X1 is area. This is the first feature. X2 is bedrooms. How many bedrooms are there? X3 is how many bathrooms are there, right? And these features basically help us determine the price of the house, right? Can you observe that um, if you have high area, right? If you have a very high area, you basically have a very high price also, right? Also, I think number of bedrooms also is giving you a very high price, right? So these, the final label is now dependent on multiple features for the prediction, right? It's not coming from a direct one attribute, it's coming from multiple features. Clear? So there'll be some combination of these three labels or these six labels. It'll give you uh, the final prediction of price, right? Clear? All clear? Fine, right? Okay. Okay. Now, these are using, I said we will be using superscript to denote features, right? How many data points are there? Can you tell me? How many data points are there in this? Others, please count. So every row is a data point, right? Right? So 10 data points, right? 10 data points. What is the value of X superscript 1, subscript 3? Okay, most of you have answered correctly. Shubham, can you look at it again and see what is X31? So X3, right? So I'm talking about, good. Okay. So fine. That's why I wanted to give you this exercise. So X1 is basically area, right? And X3 is basically third data point, correct? So what is that? So this particular feature and this particular data point, right? This data point, right? So this is the value, right? So this is X31, fine. So I'm hoping you are clear with the terminologies now or the notations. So this is tabular data, right? And this is a regression problem, okay? Can you see that the values that I'm predicting are not a class? You can say that these are classes, right? You have like 1 million, 2 million classes, but I could have predicted it like this also, right? I could have said 0.5, right? So I'm now not predicting a class. I'm not binning them into a class. I'm actually predicting some number, right? So I'm predicting some number, and there is no classes associated with this number. Okay, so some real number I'm predicting, and it can take values from say 0 to any uh, house will not be priced at negative. So it can take values, and let's say that at least there will be $100 or 100 rupees. So let's say that the value can range from 100 rupees to maximum whatever, right? So that whole thing is your range from where the Y can come, correct? So here I'm no longer talking about classes, right? No longer binned into classes. And I'll give you one example. I'm pretty sure you guys will not be able to do that. And if you're able to do it, I'll be very happy, right? Okay. So Rohan is asking, so he's given us a scenario that suppose that your Y is, if it's between 0 to 50,000, then probably will say low priced, right? And if your price comes from say 50,000 to say 1 lakh, right? This is 1 lakh only, right? This is high priced, right? Right. So this particular thing is basic. So here till here you will do a classification problem. Oh, sorry. Till here you will do a regression problem, right? Till you are predicting it. So it basically depends on what your model is predicting. Okay. So if my model predicts this Y problem, right? If it predicts this Y, it will be regression. If you have a logic inside which does this, which is not part of your model, again your model will predict at least this. So we'll treat it like a regression problem, and you'll write some logic on top of it to make it look like a classification problem. Okay. So the question he was asking me was whether this is a classification or a regression problem. Classification or a regression problem. Okay. So it's actually both, kind of both. You do it, we actually do it many times. But this part, right? This basically will be coming from the model. This much is something that you will do. This will be like a ML model. So this will be a machine learning model. So it will be treated as regression problem while solving it. Like when you will be training this, you will train it as a regression problem. This is some logic that you will write on top of it, right? So eventually it is actually classifying it into two different classes. But what are you doing with the model training? How are you modeling this? You will, till here, you will model it as a regression problem, right? So probably you will use linear regression or any kind of regression problem here. And then you will write some if Y is greater than like predict. So you will use this logic. Y pred is greater than 50,000. Then you will say high priced. Else you will say low priced. Right? So I will still say that this is a regression problem. On top of it, you are writing the classification logic. Okay, but you will still model it as a regression problem. So I'll say modeled as regression problem. Fine? Clear? Yes, no? Okay. Okay. Prediction is no longer a fixed class. We agree that it can take any number from say 100 rupees to say 1 million rupees. Right? So it can take any value, like any real number, positive value it can take. Right? So it's no longer restricted to a class. One can argue that I will make every integer a class, but I can still argue that what if there is a 0.5 there, right? How many classes will you make? Because there are infinite, countable infinites between two numbers, right? How many classes will you make, right? So that cannot be a classification problem. If you're predicting a number between say greater than 100 to up to some millions or billions, it's a regression problem. Fine. Even if you're predicting a number between say 0 to 5, right? 0 to 5, and the number can take value 1.1, 2.2, right? And all these things, right? It's a regression problem, right? Also, this distinction will become very less clear. Like, I think, Rohan, what you were asking, right? You will see it in something called as logistic regression. Logistic regression is like you predict value from 0 to 1, and you then label it yes or no. So it is a classification problem, but the name itself is saying logistic regression, right? So it's kind of an anomaly, but it's a classification problem, right? Because eventually you say yes or no, and that logic is not like a if else kind of a thing. It is actually kind of a if else of a thing, but you can actually use a regression problem and model it as a classification problem as well. So there will be cases, for example, here I will say it's a regression problem because you're predicting a number between 0 to 50,000 or 0 to 1 lakh. But if you're using a logistic regression kind of a setup where you're predicting number between 0 to 1, and then based on that number, you're taking a decision on class, that's a classification problem. So many a times your distinction between regression and classification is not that clear. Okay, so it can happen that you can act, and I have done this. Okay, so I have trained it like a regression problem, but I have done classification finally, right? So it can happen. These are some different. So what you should focus is on the algorithms that you're getting and how you can use that, right? So Bharat is asking discrete data point, variables, regression, continuous data points, variables, classification. Bharat, I think you said the reverse. Okay. So whenever you are basically kind of predicting continuous kind of a data, then you are kind of doing regression. When you're trying to do discrete binning kind of a thing, then it's classification. I think you said reverse of it. Yeah. Cool. But again, that distinction is not always clear, okay? So it can happen, and you will see this in the logistic regression. The name is logistic regression, but it's a classification problem. Okay, so it can happen that the distinction is not very clear. Fine. Now let's come to some quiz. Now you have to tell me whether it's a regression problem or a classification problem. So I have given experience, years of experience. So I have just one feature, right? So this is the one feature of year of experience. And I'm predicting salary, right? Regression or classification? Okay, everybody please let me know whether it's a regression or classification. I have only 3 answers. There are 6 people in the call. Okay, who is left? Left. Shubham, it's a regression problem or a classification problem? I think he's away. Okay, it's a regression problem, right? Because I'm trying to predict salary, right? Salary cannot be binned, right? So salary can be anything, right? Once you go to IC or IIT, you will be earning in lakhs, right? Or maybe crores, right? So regression problem, this is a regression problem. Everybody was right? Correct. Now tell me this, is this classification or regression? So this is a very famous data set. This is called MNIST. 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 So these are, each of this is a data point, okay? So these are handwritten digits. I'll tell you a little backstory, very popular data set, okay? So US Postal Services. So US Postal Services means like the post office. They wanted to automate the method, like segregation method based on PIN code. Okay, so they have a zip code, we have a PIN code. So they wanted to do some automatic I'll say automatic PIN segregation, PIN code segregation. Okay, so now all the mail letters were handwritten, right? Whatever addresses people used to write, They were handwritten. So they thought that let us train a machine learning model. And this is very old, right? This is, I think, 1990s they started. Pin code segregation. Right? So so each of this digit is an image. Okay, so this is an image. Right? Now my model will predict which digit it is. So either is it a classification or a regression problem? So it's predicting what number is this. Others, I have only two answers. Okay. Okay. Kavesh, quickly, please reply. Okay. Shubham. Okay, many of you have answered it correctly. I thought I'll be able to put you off from this, but you have understood well. Okay, so this is a classification problem. How many classes are there? Okay, 10, right? So 0, 1, up to 9, right? So 10 classes are there. So each of this digit is actually being predicted. And currently the model is doing the best model that we have to predict this is doing better than humans on this data set. Okay. Even there are digits where humans are not able to predict it correctly. For example, this, right? It's not very clear, right? It looks like a 4, right? So we don't know. So things like these machines are doing better than humans right now. Fine. And hence, whatever we are doing in machine learning is going to help us do these things. Now, I don't have to manually read it, check the address, it will automatically detect. Obviously, there are errors. It's not 100% of 100% perfect, but so are humans, right? Humans also make mistake. But currently, the models that we have for MNIST are doing better than any human. Okay, so that's a good thing. Okay, now tell me. So I have to predict the happiness index. This is my Y. Okay. And how many features I have? Number of features. I think Bharat, you got confused with number of data points and features. Okay. So data points are 8, right? So this is 1 data point. This is 2 data point. This is 3 data point, 4, 5, 6, 7, and 8, right? And these are features. So this is X1, this is X2, this is X3, X4, X5. Don't make these mistakes in gate, okay? There are 6 features. This is prediction label. Y is prediction label, right? So this is not a feature. This is a label. Good. So there are 6 features, 8 data points. It's a regression problem or a classification problem. Okay. Like, yeah. Okay. Most of you have answered it correctly. Fine. So this is a regression problem because I'm trying to predict a number value between 7 point, like between sevens, right? So you can see that Finland has the highest happiness index. People are really happy in Finland. Nice. Cool. Okay. So this is basically, so suppose that I have this algorithm that I have used to basically put emails in my box or a spam folder, right? So this is an algorithm, right? This data will be text data, which is unstructured data. unstructured because there is no structure like a table into it, right? So is this a classification or a regression problem? Classification, right? Right. So there are two classes, whether it's a spam, not spam, based on that. So this is not spam. It'll send it to my inbox. If it's a spam, it'll send it to a spam folder, right? So it's a classification problem. Classification problem. Fine. Okay. Now this is basically this is also another data set, and they really use this. So this is the flower, okay? And based on some features like this sepal length, width, petal length, they used to predict what kind of flower it is. Okay, so this is flower prediction, flower breed. I don't know. It's not breed. I think. I think here will be able to answer better. This is flower type prediction. So is this a classification problem or a regression problem? Yeah, species prediction. Correct. So you basically tell which species is this of the flower, right? So based on length of the sepal and the petals and the width, you basically predict whether it's Setosa or versicolor or Virginica, right? So it's a class. What problem is this? Classification, right? Now you guys are understanding the difference between classification and regression. Fine. Okay. Now I'll ask you multiple questions, right? So this is my data and I can choose to predict any of the features, right? Or any of this column, right? Now let me try to uh, predict this diastolic. Okay, diastolic means is your heart pumping well or not? Like how well your heart is pumping. And this I actually worked on diastolic versus systolic prediction. Uh, Tell me, is this a classification or a regression problem? So this is a prediction. This is why test all or your features. Regression or classification? Huh? Okay. Bharat, why is this classification? Okay, let me add this. Okay. So this is 2.5. Probably you are getting confused with integers. So you will say that I can make this as an integer between 1 to 100. You can see maximum 100 here, right? Now suppose that there is a 0.5 here. Is this still a classification problem, Bharat? All right. So it's a regression problem. So let me call this regression. Right? I'm trying to predict a number between, say, actually it will not go beyond below 40. If it's going below 40, matlab you are dying. So I don't know what is wrong there. Yeah. And even a higher number is a problem. Fine. So it's a regression problem. Okay. Now I'm trying to predict the glucose levels. Okay. So this is glucose levels that I'm trying to predict. It's a regression or a classification problem. So this is glucose levels. Classification, regression again. Fine. Right? Regression problem. Because I'm trying to predict some glucose level, right? Same if I wanted to predict the hemoglobin level in your blood, it'll again be a regression problem. Okay. Now I'm trying to predict the BMI. This is simple. Regression again, right? Fine. I'm trying to predict the BMI. Okay. I'm trying to predict whether the person has diabetes or not. Okay, cool. This is classification. Correct. Yeah, only class. I think only, yeah. Only this can be a classification problem. Yeah, fine. Okay, so that's bring me to the end of the lecture. Fine. So that's all I wanted to cover today. So what we have talked about is we have talked about what is machine learning, how humans learn, and how we are trying to mimic that to train the machines or say computer or a robot. Always, I think it will make more sense when you talk about teaching a robot rather than your laptop. So whenever you have to imagine that you're teaching somebody, some machine, think that you're teaching a robot. I think it will make more sense to you if you're new to machine learning. Then we talked about why machine learning has emerged, and we talked about the digital revolution that happened, and it gave us like enormous amount of data, and we are able to use that data to learn, right? Because we need data to learn. So digital revolution has played a huge role in emergence of machine learning and why is it becoming so hot right now, right? Then we looked at different types of machine learning algorithms, which were supervised and unsupervised. Like the classification, there are three types of algorithms, but we are going to only learn supervised and unsupervised in the GATE syllabus. So we talked about supervised, and supervised basically has two types, classification and regression. So we have looked into how classification problems look like and how regression problems look like. Obviously, it's not always distinct, it's something that we have learned, but mostly we'll be able to distinguish between a classification and a regression problem. Fine. So that's all I wanted to cover today. Thank you. I will see you in the next lecture.